Thank you. Thank you for the introduction. Thank you for the invitation and for the opportunity to give a talk at your seminar. So I will talk about the Allen-Cahn equation with critical initial conditions. This is based on two works. One previous work with Martin, who is at the PFL, and Khoa, who is in Leeds. And then the work that I'm actually going to talk about, which is a work with Simon Gabriel, who used to be a PhD student of Nikos and now is a postdoc in Münster. And Nikos is here in Warwick. Okay, I will try to explain to motivate the question a bit in the first few slides, and then I will explain to you our main result, and I would like to finish with a bit of an outlook on an ongoing project. Feel free to interrupt me whenever you want to ask questions. I'm very happy. I'm very happy if you have any questions or comments. So the setting is the following. We consider we will talk about stochastic PDEs, but actually we will work with the deterministic PD. So we will work with the Allen-Cahn equation, which is the following. So it is an equation which has a component which has the heat equation, and then you have some sort of nonlinear term. In this case, we have some linear bit with a parameter m, and then a cubic nonlinearity, and this is set sort of on D-dimensional space. And we are particularly interested in the case in which this parameter m is positive. When m is strictly positive, this u minus u cubed, this sort of minus the gradient of one of the most studied potentials. So you have this double well potential with two minima. If m is strictly positive, in this case, if m is 1, you get exactly plus and minus 1. So we will be interested in the case where you have this double well potential, and in particular, we are interested in the case of two dimensions. So the results that I explain actually hold also in higher dimension, case where you pass from being critical to being supercritical, but one has to modify the scaling in a somewhat a natural way, so I will not discuss this. So if we look at the two-dimensional case and we look at the solution to this equation, at least for value either plus or minus 1. So the solution will sit in one of the two minima of the potential. Essentially this minima you will have regions in which you are close to one minima and regions where you are close to another minima, and these regions will be separated by an interface, which in this picture could be this. And there is an effective dynamic. So essentially you can reduce on large scales the entire dynamic of the PD to the dynamic of the interface that separates this set. So at large scales, this dynamic is described by mean curvature flow, and there are many other models which have other sort of phase field dynamics. What interests us, the thing that motivated us to start to study these problems, even if then in the end we are not able to provide any information in this regard, is the study of sort of long-time properties of this phase field dynamics, so of this mean curvature flow. So to give you an idea, I could try to share something else. Let me see if I manage. So now you should see. No. You should see my my web browser. Now you should see some kind of simulation of this process. So you have so these are these regions that I was telling you. Here, for example, the blue could be +1, the red could be -1, and these regions evolve according to this mean curvature flow. So essentially things tend to shrink, and what you observe, and okay, when it restarts, this becomes clear, is that if you start with some sort of a very mixed initial state, after some time you develop larger and larger regions where you are either close to one or close to the other minimum. So the typical distance that you observe kind of tends to increase in time, and this is called coarsening. So let me share again my iPad. So now you should see my web browser. Now you should see some kind of simulation of this process. So you have so these are these regions that I was telling you. Here, for example, the blue could be +1, the red could be -1, and these regions evolve according to this mean curvature flow. So essentially things tend to shrink, and what you observe, and okay, when it restarts, this becomes clear, is that if you start with some sort of a very mixed initial state, after some time you develop larger and larger regions where you are either close to one or close to the other minimum. So the typical distance that you observe kind of tends to increase in time, and this is called coarsening. So let me share again my iPad. Sorry, this takes a second. Okay. So what is kind of expected is that if you start your mean curvature flow in some sort of initial state, which could look something like this, and then you run it for long times, you will see sets that become very large. This is called coarsening, and the size of these sets is conjectured to follow some sort of scaling law. So in 2 dimensions, this should, for example, become of size sort of square root t. So in principle, you would expect that there is some sort of self-similar object which should appear conjecturally if you start mean curvature flow and then you rescale it according to some scaling which is described by this law of these laws of this coarsening. Now this is all incredibly conjectural. And one of the reasons why it is conjectural is that actually does not happen every time you start mean curvature flow. So there are simple examples. If you start mean curvature flow in 2 parallel lines, these are fixed by the dynamics, and this distance, the distance between the two lines does not increase over time. So in order to see sort of this kind of coarsening or scaling, one would like to start mean curvature flow, and one would like to start this phase field dynamics in some kind of generic initial condition. So this is sort of what motivated us. So our purpose is to kind of study these dynamics when one starts from some reasonably generic initial state. And the first question that we kind of try to answer is what would be the right sort of choice of an initial condition for mean curvature flow. Just as a reference for this sort of long time properties of phase fields, I think the only mathematically rigorous one is the result by Otto and Cohn, where they kind of prove they kind of prove upper bounds on the coarsening rate. So the distance cannot be larger than square root t, but it can sort of be smaller. And this is because it is sort of a deterministic argument. And so we will now sort of start our equation in a random initial state. And then we would like to see, in some sense, what happens to mean curvature flow starting in this initial state, but we'll immediately incur in some problems. So the natural thing to start the equation with is some kind of totally mixed initial conditions. It's a little bit close to what I've shown you in the picture. It's something where sort of at every point you choose whether you're kind of plus or minus 1. This would be kind of the natural or somewhat universal initial condition that you would like to choose, and this would correspond to something like white noise. However, when you start with something that is very regular, you introduce some you introduce some sort of difficulty in solving the equation. And in fact, in 2 dimensions, as I will explain in the next slides, starting sort of in space white noise means sort of starting in the critical space of initial conditions for the equation. So there is no real solution theory for any of these equations, starting from your sort of randomly chosen, totally mixed initial condition. Okay, so this is a bit the motivating aspects of what I've done, and I will try to explain to you the problem that we are concretely looking at. So we are taking the Allen-Cahn equation and we're starting it in white noise. White noise is a Gaussian random field, which means it's centered actually. So it's Gaussian centered and it's described by its covariance, and its covariance structure is a Dirac, which means that it's chosen independently at every point in space. And white noise satisfies some kind of invariance, which is just a 2-dimensional version of the invariance of the scale invariance of Brownian motion. So this is the invariance written down. And the fact that white noise is invariance makes you guess that actually also a solution to the Allen-Cahn equation started in white noise, which should lead to some of these phenomena that we saw in these pictures. Also, that solution should satisfy some kind of scale invariance. And in fact, this is the scale invariance that the solution should satisfy. So here epsilon is kind of a small parameter. So what you're doing is you're zooming into at small scales into your equation. And what you expect to see is the solution of the equation itself. So if you zoom in distribution, you should see the same equation. This is sort of scale invariance. And in fact, one can check that this is the case. So if now we have chosen this particular scaling, the scaling is chosen such that in space and in front of the solution, you have the scaling of white noise. So this is exactly the scaling of white noise. So this is a scaling that keeps at time zero the initial condition invariant. We have chosen it exactly in this way. And then time and space are sort of scaled parabolically. And in this case, the heat equation is kind of preserved under this scaling. And you get an epsilon cubed in front of the right-hand side. And this cubed is exactly the same of the power of the nonlinearity. The linear term is now not important at all. So it's the scale, the criticality is provided just by the nonlinear bit of the equation. So I've forgotten the linear bit immediately. And this is sort of exactly the same as minus u, the rescaled function to the power 3. So what I have just done is said that, well, I sort of zoom into my look at my solution at small scales, and what I see is actually again the solution to the same equation that I started from, and from the perspective of trying to solve. So we don't actually know whether there is a solution or not to this equation, and from the perspective of solving this equation, this is a problem. Because the typical or the classical sort of theories to solve this, PDEs or SPDs rely on the fact that on small scales you essentially see a heat equation and you don't see the nonlinear bit. So this is called subcriticality, and this is what lies, for example, behind the theory of singular stochastic PDEs. So you always have an equation where when you look at small scales, you see something linear, or you see somehow the heat operator being the dominant bit. Of course, there are theories that go beyond sort of subcriticality. For example, there are martingale methods that are used for super processes, or there are many other sort of supercritical or critical equations that can be treated. But martingale methods don't really apply in settings such as this one, where you have a random initial state, so where the noise is not sort of time dependent. So really, there is no real idea of how to make sense of the equation. And what I will talk to you about is sort of some kind of weak study of this problem. So we will not solve the equation, but we will sort of try to look at some certain Gaussian fluctuations that appear if you rescale the problem in some non-trivial way. Another way to look at this whole picture is to look at it in terms of regularity of the initial condition. So one can look sort of at the line of regularities alpha. So alpha is now the regularity in terms of some, if you want, Sobolev or base of space. Actually, it should be sort of L-infinity-based base of space that you can choose. So if alpha is 1 million, it means that your function has 1 million derivatives. If alpha is -1, it means that your function is one derivative of something that is more or less just barely, it's just continuous, or it's just barely a function. And so if you start with something smooth, the Allen-Cahn equation is perfectly well posed. But then the more you make the initial condition irregular, the less it becomes well posed. So you can become sort of, after zero here, you become genuinely a distribution, and then still you can make sense of the equation up to some point. And there are two thresholds here. One threshold is this -2/3. It's the one at which you will, just by a calculation that is probably 2 lines long, you will end up having a problem when you do sort of try to apply Picard's theorem, or Schauder estimates, which are the regularization estimates associated to the heat equation. So the issue is you want to start with something that is not a function. You look at a slightly later time when you have to take it to the power 3. So you have to have it as a function. And then you say, okay, well, it will be a function as long as I kind of pay a price in terms of blowups in time, because in the meantime, the heat operator will have smoothed my initial condition. But the price you pay in terms of blowup in time must be such that if you take it to the power 3, it's still integrable, and this leads exactly to this condition of -2/3. So the 2 comes from the parabolic scaling, and the 3 is exactly the 3 from this power here. So kind of until -2/3 or just above -2/3, you can just use the classical PDE theory or just Schauder estimates to solve your PDE. And then below -2/3, there is now a gap. So there is a gap because the actually interesting space is the space, say C minus one, so where you are a derivative of a function, and this is the space in which white noise lives. And it's interesting because it's the scaling critical space. So through a scaling argument, you can see that actually for any initial you would sort of expect that for any initial condition which is more regular than minus one, you can solve the equation. And this is sort of an equation-dependent thing. So in some equations, these two numbers are the same. For example, in the Navier-Stokes equations, you get that the critical space, the scaling critical space, is exactly the one above which you can actually solve the equation with mild solutions locally. But in this case, they are separated. You can still bridge the gap, and this is what we did in. It's a reformulation of what we did in the previous work with Martin and Khoa, where we kind of well, you sort of can solve the equation as long as you start in some white noise initial, in some Gaussian initial condition. So you use the fact that the initial condition is random, and then you run sort of a scheme which is reminiscent of a scheme of sort of these singular SPDE schemes. So you kind of try to guess the first few terms in your expansion of your equation, then sort of the whole rest will kind of be controlled because things get better in some sort of sense, in the meaning that sort of things become more and more regular as you do an expansion that actually I will explain towards the end of the talk, an expansion in terms of the initial condition. Okay, so this sort of regime can also be covered, and you can actually solve the equation. I should mention that this was also done in sort of some generality by more recently this year by Ilya Chevrev and a PhD student of his. And this leaves us with sort of the one point that is more sort of the most interesting one or the most special one, which is the case where you have a critical initial condition. And this is the one in which we work in. And as I mentioned, we will not solve the equation. We will study a so-called recoupling limit, which means that we study some sort of Gaussian fluctuations. So this is the result that I will present to you. We consider the Allen-Cahn equation. And we have now introduced in the Allen-Cahn equation two parameters. One is the coupling constant lambda, this lambda here, it's positive. And then we have introduced the parameter epsilon, which is a smoothing of the initial condition. So Xi is our white noise. Xi is very regular, but now I have modified it, and I've modified it on a spatial scale epsilon. This PT is the heat semigroup, so P epsilon squared is a modifier at spatial scale epsilon. And then I have coupled, so once I make the initial condition smooth, I can solve the equation. So this U epsilon exists, and the question is what happens when epsilon goes to 0. And now I couple the smoothing of the initial condition with the coupling constant in front of the nonlinearity through a logarithmic rescaling. This is called the weak coupling because in the limit as epsilon goes to 0, the coupling constant will vanish essentially. So you will just be left with a linear equation. And in fact, this is the whole point. The whole point of critical equations is that somehow exactly this does not happen. So there is something non-trivial that happens. And the non-trivial thing that occurs is that, well, if this was a completely well-posed system, as epsilon would go to 0, I would sort of find myself with an equation where this nonlinear term is not there, and the initial condition is simply white noise. So I would just see sort of the heat semigroup applied to white noise. And the result that we prove is that you see exactly the heat semigroup applied to white noise, and there's an e to the mt, which is just due to this linear term here, which is not important, so you can set m to 0. So you see exactly what you expect, but you see an effective variance, sigma, which depends on the coupling constant lambda that you have put here, which is not 1. So this sigma lambda has an explicit form, and it's strictly smaller than 1. And this is the whole point of this recoupling limit. So it's a way to sort of recover some effect of the original critical system in some sort of regime in which you somehow in the limit see something linear, so something that you can treat. But the way that you recover it is through some kind of effective variance that appears in the limit. And this result holds for coupling constants lambda that are sufficiently small, and I will address this in a minute. And I think in the way it's stated in the paper, we have also some constraint on the time horizon until which we can go, but this constraint is actually completely irrelevant, so we can actually work without it. But this constraint that the coupling constant is small is not irrelevant. So this is because we use a perturbative argument for our analysis. So let me make, if there are any questions regarding the statement of the main result, please ask me. Otherwise, I will make some comments regarding the result. So the whole point of the result lies in this effective variance sigma lambda. So the sigma lambda is strictly smaller than 1, which means that the nonlinearity is marginally relevant. And the particular form that it takes is not completely by chance. So it appears essentially as the solution of an ODE in the coupling constant. And this ODE is exactly linked to the nonlinearity of the equation. So the ODE in the coupling constant is minus f cubed, where the cube is sort of this cube that you see here. And then there are some kind of combinatorial factors, this 3 over 2 pi, that just make it, that just appear. So up to some combinatorial factors, you're just looking at an ODE which is determined by the nonlinearity. But it's not at all clear why this ODE should appear. So this is something that I will explain in a few slides. It's not at all clear why, sort of in the limit, you should see an ODE in the coupling constant. This is some kind of homogenization argument. Finally, we have this constraint that the coupling constant has to be small. The reason for this constraint is that we use a perturbative argument. So we kind of expand our solutions in powers of lambda. And you can, as an analogy, think of sort of expanding the solution to this ODE in powers of lambda. And if you do this, well, the series that you get has a radius of convergence within which it converges absolutely, and this radius of convergence does not see the minus sign here. So the radius of convergence for the Taylor expansion of this ODE is 1/2, because 1/2 is the explosion time of the solution to this ODE when you have a plus sign. And this is the whole error that we do. So somehow we are missing the minus sign. So our perturbative argument puts absolute values inside the sum. We are missing the minus sign, and so we see sort of some finite time blow up. So this constraint is sort of technical, but it's really there. So you have to do something so we don't expect it to be there because we have this minus sign. But you really have to work to remove it, and we don't know how to do this yet. Okay, so this is important also in comparison to other works. So there's a bunch of systems in which critical equations, situations in which critical equations have been studied. Let me mention here sort of linear equations with multiplicative noise. So perhaps the most recent and most comprehensive works are due to Caravane, Sun, and Zygouras. And then there are some results by Dunlap, Khoa, and Graham that treat also nonlinear equations. So here you have a similar behavior. So you study with coupling limit. And the tools are actually also somewhat similar, because you will see that we do some kind of expansion in the coupling constant lambda, so there is some perturbative expansion. The main difference is that in terms of the result is that in this setting there is a phase transition. A phase transition means that actually the scaling limit should not hold for all lambda, but it should hold for lambda. It does hold only for lambda up to some finite value, and then there is a critical value of lambda at which you see something else kicking in. And this you can see from the fact that the variance actually in their case kind of blows up at some critical value of lambda. This is not the case for us. So for us, this variance never blows up. So our guess is actually that there is no phase transition that appears. And of course, apart from the fact that we use perturbative arguments, I think that there is no real similarity between the tools, because we don't have really martingale. We now have no martingales available. We don't have any. So the analysis is a bit different. And there's a second set of equations that have been studied extensively, which are equations which have a white noise invariant measure, but which have an additive noise as well. And these are sort of KPZ type equations in 1 or 2 dimensions, Burgers type equations. These have been studied by Toninelli, Cannizzaro, Gubinelli, and so on. And here the tools are completely different. So here one uses tools from the theory of Markov processes, actually. And our solution simply is not a Markov process. So this is a bit of a different approach. Other than these 2 cases, there are actually not so many. So of course one can come up with some sort of super processes, for example, are supercritical stochastic PDEs that can be solved completely, but there are actually not so many critical or supercritical SPDs that can be studied. So one of the interests in this work is that you can say, so just saying anything about critical equations is somehow interesting. And before I move sort of to the proof, let me mention that actually weak coupling limits are a bit funny. So the theorem tells you that if you rescale the coupling constant correctly, you see some sort of limit. This would kind of tell you that in some sense it's necessary to rescale this weak coupling constant. So if I rescale something and I see a limit, it sort of suggests that if I don't rescale something, then things should blow up. But this is not the case. This is some kind of strange behavior. So for example, it is a fact that if you just look at the equation without any rescaling, then you have an a priori estimate on it. This is an estimate that is uniform in all initial conditions in L infinity. So you can actually conjecture that there is some kind of self-similar limit in 2 dimensions for this system, which should appear as the limit of the solutions as the smoothing goes to 0, and somehow tightness is given to you for free for this system. So the only thing that is left to prove is kind of that there exists a unique limit in law, but of course we have no idea of how to prove any of these results. But I think it's sort of important to remark that there is something arbitrary about the weak coupling limit. It's something that sort of bridges between subcritical and the critical world. So it tries to look at these critical systems from the perspective of subcritical equations. So it sort of tries to control things that tend to explode. But it's perhaps not necessarily it's one way to look at these systems, but it's perhaps not the only way, and it's perhaps also not the best way. It's not the most physically relevant. Perhaps this is the solution to this equation should be the physically sort of most relevant one, but we don't know how to approach it. Okay, so again, if you have questions, please feel free to ask. Otherwise, I will pass a little bit to the solution theory, to our proof approach. So essentially, we can forget about the linear term in our equation. We can just look at our weak coupling system, our Allen-Cahn equation with our smoothened white noise initial state. And then what you can do is try to guess the shape of the solutions in terms of powers of lambda. And this is relatively easy. So first of all, when lambda is 0, this nonlinear term is not here, and everything you see is just the heat equation. So the heat operator, the heat semigroup applied to your initial condition. And there is a neat graphical way to represent now this term and all the successive terms in our expansion, which sort of link to trees. So you can represent with a dot the presence of a noise psi, and then once you convolve it with the heat semigroup, you kind of draw a line down. Okay, for this linear Gaussian term, this is not so interesting, but now you look at the sort of next order term, the term which comes from the nonlinearity, so the first order term in lambda, and this here the contribution comes from when you put sort of this Gaussian term inside the nonlinearity, so you cube it, and then you again convolve with the heat semigroup. And what you get graphically is something like this, where we have taken the cube of our Gaussian term, and we have just said that, well, if you take sort of three trees and you evaluate them at the same point, they look like 3 copies that sort of merge together at the root. And then we have convolved this with our heat semigroup, so we kind of end up with a tree that looks like this. So it's trident with which is planted at the bottom. And then you have the second order terms. And you can write down sort of all these terms in these expansions as trees. And they come with a certain power of the coupling constant in front. So of course these terms become terribly complicated, and unfortunately our proof works by sort of analyzing these terms uniformly, so this is a bit nasty. However, before I explain to you what we exactly do in the proof, I want to give you the heuristic of how our limit should appear, which is a very nice heuristic. It would be even nicer if we would know how to turn it into a theorem. So what you observe, okay, so you look at the first few terms in your expansion, and you just try to check to see what happens to these terms in a weak coupling scaling. So you look at them, and you just observe that actually, so these guys, they all come from some Gaussian random variable. So this means that this is a cube of a Gaussian random variable. It will live somewhere in the third homogeneous chaos and in the first homogeneous chaos, and so on and so forth. They all live in they have always components in different homogeneous chaoses. But what you observe is that's actually only the first homogeneous chaos. It's only the Gaussian component that contributes to your limit. So this is very special of this system. It's not the same for all critical systems, by far not the same for all critical systems. But in this system, it's really just the first chaos component that contributes to your weak coupling scaling. So then you can kind of guess that the effective dynamic of your critical equation is described by some sort of projection of your equation onto Gaussian random variables. And if you do this, you quickly end up with a guess for what the equation should be. So you assume that your solution u here to this equation is Gaussian. Now you cube it and you want to project it down to Gaussians again. And you know exactly how to do this. So if you do this, if you take something, a cube of a Gaussian, the first chaos component is just 3 times the expected value of the square times the Gaussian itself, or you can view this in many different ways. So you can write down an effective equation, which is some kind of Mekin-Vlasov equation, in which you have sort of averaged out the square. So you have rewritten the cube as the average of the square times the function itself, and then there's a combinatorial factor 3 that appears in front of you. And this is nothing else but sort of trying to project the whole equation down onto the first chaos component, down onto Gaussian random variables. So you can try to guess that this is the right equation, and in fact, it sort of looks like this really should be the right approach, because from here you can sort of deduce what the effective variance should be in the limit. So the way in which you deduce the effective variance is that you say, okay, this equation now has actually a Gaussian solution. So if you start with a guy, if your V naught is Gaussian, V epsilon 0 is Gaussian, then essentially this equation is well linear, and this term will be sort of just the coefficient, because you have taken the expected value of something, will just be a constant in front. So the equation will stay, so you start somewhere Gaussian, you stay Gaussian. It's kind of linear up to some rescaling of the variance, that's it. So everything that's interesting in this equation is what happens to the variance. And essentially, the variance just follows the ODE associated to this problem. So it's a variance that evolves in time. It depends on the coupling constant lambda and on the parameter epsilon. And it will just solve the same ODE that you see here. And now the expected value of the square, well, it will be this variance squared times you will have the heat semigroup applied to the white noise, and this will give you 1 over T. So the blow up of the heat semigroup of the heat kernel into dimension is 1 over T. This is exactly this 1 over T here. And this is what gives you criticality. Here you can re-see criticality. So this is 1 over T, something that blows up at time 0. So if your variance at time 0 is 1, now you look at the later time, and you are integrating 1 over T from 0 to 1, let's say, or to some arbitrary small parameter, and you will get the logarithmic blow up. And this is compensated by your weak coupling. So the weak coupling is there to compensate the logarithmic blow up, and it gives you a first order term in terms of powers of lambda. And when you do this, you see, first of all, you see that there's a series expansion that appears for your effective variance. And also there is a procedure by which, so the original effective variance at scale epsilon and with coupling constant lambda depends on time. but the limiting one is independent of time, really. So it's just a function of lambda. And sort of you're kind of switching in a weird way time and lambda in this equation when you pass for epsilon going to 0. So you end up with actually the solution to this ODE where time is replaced by lambda, essentially, and these guys disappear. So this is how you can guess the effective variance. Okay. So let me say a few things about how we act. So we are not able to make this, to turn this into a proof. Our proof follows a much cruder approach, although I think there is something to this approach that is more general, and I will say this just in the very last sort of outlook slide. The approach is to look at this equation 3 by 3 and decompose it into different sort of chaos components. And then to try to identify essentially, for example, if we look at second moments, so if we look at the second moment of a tree, this will correspond to two copies of the tree with different contractions. For every sort of contraction among its leaves, you have a piece of your second moment, essentially. And what we do is to try to identify graphically which contractions contribute to this weak coupling limit and which contractions do not contribute to this weak coupling limit. And it turns out that a contraction contributes if one can iteratively remove sort of these small loops. So this is a bit of a, so I think this is somehow one of the interesting things is that one can find, so this description is purely graphical, whereas the original description, so there is some sort of graphical structure that appears in when you try to describe how the contribution to the limit appears. So let me try to compute this one example for instance. So in this case, what I would like to highlight is that you always can remove one of these guys. So here you could start with this equation, with this tree, and then you would end up with somehow, if you blow up this one loop, you end up with something that actually looks like this. Okay, so this looks essentially again like a one loop if you compute it at the same point. So the defining property of contractions that contribute to the limit is that one can extract iteratively always one further one loop until the whole tree is completed. Whereas contractions such as this one, where there is no one loop to extract, they contribute less, and you have to do some kind of estimate to show that in fact it's the case that when you see something like this, so a two loop or a three loop, then this will sort of give you a contribution which in powers of log epsilon is less. And this is something that is possible in this case of initial data because we can use some sort of L1 L infinity estimates. So it's a relatively, turns out to be a relatively, it's not a too complicated procedure to show this. And in fact, it's necessary that it's not too complicated because to complete the result, there is one last step, which is the most annoying one. So now we kind of know that each term in terms of each term in the sort of decomposition in terms of powers of the coupling constant, each term in my perturbative expansion sort of contributes to something. However, I kind of have to control an infinite number of them, so I have to manage to sum them up in some reasonable way. And the problem here is the following. So you would like to approximate your solution with some cutoff version of your expansion. So you you consider only trees up to some, some large number n, and then the rest should be of order lambda to the power n and should sort of not matter. But what you cannot do is kind of pass first the limit as epsilon goes to 0 and then to the limit as n goes to infinity. So it's not enough to look at a finite number of trees, show that the limit there is a limit as epsilon goes to 0, and then from this conclude the limit of the whole series. Actually, you have to couple you will have to couple the size of the modification with the number of trees that you consider. And the right coupling with them is that turns out to be logarithmic, so you have to consider log epsilon inverse trees. And the problem is that now you will have a very large sum. For each term in the sum, you will know that it converges to something, but you also have to take care. So the typical problem with these kind of expansions, which are called wild expansions, is that a single term in this expansion will have, so if I look at the term of size n, there will be sort of n factorial or 2n factorial contractions associated with it, with each trees. And if you do a bound in the wrong way, you will end up summing up n factorials too many times, and the sum will never converge. This is sort of what destroys your wild expansion typically. So you have to really take care of the fact that you have a very precise quantitative estimate. So there is a whole filtration of contractions. There's 2n factorial ones, there's a bunch of ones that contribute and they are summable. And then there's more and more ones that don't contribute, but they also sort of the fact they contribute, so there is some decay, they go to zero in a way that balances out their number essentially. So one has to do a bit of combinatorics to bound this sum. Essentially, this is the proof. So if you manage to prove convergence of a single tree and then sort of have a sufficiently uniform estimate for a sufficiently large approximation of your wild expansion, then you obtain the result. And here we somehow use a maximum principle. So I think this is, I don't want to explain this too much. I can leave it for questions if you're interested. Okay, essentially that's it. There are a few open problems that are interesting. One I have already mentioned. So first of all, we would like to extend our results to all values of coupling constant. And this is, so there are some tools, but it's not really obvious to us how to do this. What is more clear is that, well, our result is kind of, it's a bit funny. So it looks like a central limit theorem, and I call this an effective variance. But in the limit, we actually see the same noise from which we started. So it's not a central limit theorem. This is also reflected in the fact that our equation is sort of projected down to first scale. So in a real central limit theorem, you would kind of have contributions from all chaoses that become Gaussians. Instead, here you start with something Gaussian and you end up with something you start with one Gaussian and you end up with the same Gaussian. And so you can actually study fluctuations around this. And fluctuations should be given somehow in exactly the same way by contractions that satisfy essentially the same property, that you can remove one cycle as many times as you want, but once. So once you have to lose, and all the other times you have to win, and those will give you the right limiting contractions. And the last thing, which is work in progress with Simon, is that of course, we would like to extend this to equations which are not this equation. So we would like to extend it to, there are infinite number of interesting critical equations. So you can think of 544 or the Anderson model that have never been treated, for example. So neither of these things. So this is mostly about linear equations, and this needs some sort of Gaussian invariant measures. And in all of these cases, somehow what turns out to be the case is that there is still some kind of graphical structure, an iterative graphical structure that tells you which, at the end, you will first you will have to do some renormalization, and then you will have to use a weak coupling argument. There is some kind of iterative structure that tells you which terms contribute exactly to your weak coupling limit. So the hope is that you obtain some fairly general result, which tells us at every power of the coupling constant, which is the effective variance which we see in the limit. And then whether we manage to sum this up or not is another question. Probably is the question that we will not be able to answer because it relies very much on the structure of the equation. Okay, but this is sort of in progress. That's it. If you have any questions, you can ask me. Otherwise, thank you for your attention.
Thanks for the nice talk. And are there any questions?
Yeah, I have a question. The lambda was constant, right? Is it I was just sort of curious. Can you take it to be space dependent or?
This is a good question. You can take it to be space dependent. However, I don't know if it's so easy to describe the limiting.
So you have an ODE for that, right?
Yeah. So this is a very interesting question. I think you let's see. Essentially, you would end up with something with a space-dependent lambda here, and then this sort of I think the limiting object should be described differently. I don't know myself exactly how it should be described because it's not reduced to an ODE. It's now a PDE really because it's spatial. The variance should vary in space. So probably there is some kind of heat equation type structure that should describe this. Oh, perhaps it's this equation. You see, perhaps it's just this one. So you just add here. Okay, I might be wrong because I never thought about this, but you might just have the heat equation. With this lambda. Now, of course, what happens? Okay, so it's a very interesting. So what happens to the limit? First of all, is not so obvious because you have the heat operator in the way. If you're lucky, you just end up putting a heat operator in front of this expansion. And also how to prove this is not so this is the right way to get the heuristics for lambda, and I think this should be the right equation. However, how to make this a theorem is not so clear, so we never know how to use this fact. So it's a very good question. I think one can guess the right variance, but it's not so clear that one can prove it. Thank you.
Thanks. Any other questions?
Well, maybe I could ask another one.
Yes.
When you don't scale by log epsilon, you got some conjectures. Yeah, so you're not expecting, are you expecting Gaussian things out of this or?
The one thing it cannot be is Gaussian because it's bounded.
Oh yeah, okay.
You have this uniform bound, independent of the initial condition. Yeah. So that's pretty much the only question I can actually answer about what it should. It's not really clear, even if it's not. I don't think it's actually super clear whether this object should exist or not.
Uniquely, on every sequence.
Yeah, exactly. Of course, you have tightness, so there is some limit. But then if you don't have uniqueness, it's not really meaningful.
So even at the heuristic level, that it's not known, like if it should converge or not. Like.
Yeah, exactly. So yeah, I think in 2 dimensions, it's sort of perhaps expected that there is something, but and it's related to this phase field dynamics that I was describing. But for example, in higher dimensions, I'm not sure.
So, but is there any? Sorry, yeah. Is there any relation? Like, I mean, are just these completely different problems, like the 1 and 2 and the 3, basically, or do you expect to have, I don't know, some critical? I mean, if you put a lambda in front of v cube in 3, you would.
This 1, 2, and 3.
Yeah, I mean, the 1 and 2, in some sense, have similar behavior, but like the 3 just are related, or I don't know. So.
Yeah, I think a little bit it is unrelated because you don't have both of these are with additive noise.
Right, I think that's right. So
However, yeah.
no, no, go ahead.
Go ahead, go ahead, go ahead.
No, I was saying, like, for instance, if you look at, you mentioned random Schrödinger, I don't know, if you put additive noise, then you would expect more to be close to this 1 and 2 to have a similar behavior, right? Or maybe, yeah.
You mean something like um,
Right.
something like this?
Yeah.
Yeah. So yeah, this is a very so right. So first of all, if this is so there are a few things that so if this is space-time white noise, it's probably seems very linked to this world here. However, for
Right.
example, if this is space white noise, so if you look at something like the Anderson
Right.
Hamiltonian in 4 dimensions, which is still critical, then you are a bit again out of this world because you don't really have. So all of these are a little bit martingale related. So you're out of the world in which you can do something, and
Right.
actually So this is the thing that we are kind of trying to figure out. These graphical representations still work. So you can try to. This is essentially the easiest example that we managed to treat in this work in progress. So if you look at kind of let me write the parabolic one because I'm always more comfortable with the parabolic one. So this is space-wide noise. And you are in dimension 4. Then you can sort of represent your solution. You would have sort of powers of lambda, and then you kind of have linear trees of size n. Say. So this length is n. And dots, sort of. And now you take second moments and you end up with things that look a bit like, so they essentially look like Feynman diagrams, which one has to compute. So they could look something like this, for example. This would be a typical diagram, or they could look something like something like this. So I'm just inventing a few,
Yeah.
but
Sure.
so you can sort of we actually can study the scaling limits of this in weak coupling, and you can characterize whether sort of one guy contributes. So this guy will contribute to the limit, and this guy will not contribute to the limit. Sorry, this should not be sort of. And this sort of appears from the fact that you can extract some sort of minimal graphical structure out of this. So in this case, it's this loop. This is the same thing as this loop that you had here. So this idea is completely general, and it seems to work in most cases that we study. Then the difficult thing is that one does not know how to sum things up at all. So it's a perturbative argument.
But this should give you Gaussian, like.
This gives you, the limit will be
Right.
Gaussian. This is part of the present. Yeah, this comes with the
Right.
limit and it's a central limit theorem. It's not this
Right.
weird. It's a true central limit theorem. The limit is Gaussian, and you kind of have a combinatorial description of the variance and the covariances. Whether you can sum things up is the total mass. So this is not clear. This is somewhere in between, right? So this ends up being somewhere in between here, between this world where you can sum things up, but you can only treat very specific equations. And here with the perturbative argument, and you can even sum it up because the equation is super nice.
I see.
So it's, So we're trying to go towards this additive noise case, but there's not every idea sort of extends. And you have to work much harder for these estimates.
Thanks. Anything else? Any other comments, questions?